Good afternoon. Coffee soon. So I'm talking about serverless machine learning in production. You can find me on Twitter or at galmai.com. And all this code's on GitHub too. So I build this machine learning systems at Distill Networks. We protect websites and APIs from automated attacks and bot attacks, which is sort of the motivation for this talk. So the story goes that last fall, our product owner comes to the team, and we're a data science team. We enjoy doing research and building models. Putting stuff into production is like, not our favorite thing. So the product owner comes to the team, and he's like, hey guys, the business really needs you to build this machine learning system in the next 3 months. What do you think? So we say, well, that sounds great. Just to check, are we going to have any support from like ops or engineering or security? To which product owner says no. So we're like, okay. He says, do you still want to do it? You want to try, or you want to try something else? So we kind of huddle as a team. We say, you know what? Let's try it. See what happens. So as a result of that conversation, it kind of put some engineering constraints on us. First off, we knew that we really didn't want boxes that we had to maintain, support, stand up. That whole business was not what we were interested in. We knew that we probably wanted to keep things secure, but we didn't want to be the ones really responsible for that because we would screw it up. So as much security that we could offload to other people would be perfect. And then essentially, as data scientists, we're building and training models in Python. We really didn't want to go through the process of transliterating them into some other language to be supported in some systems. So as much as we could deploy exactly the models we built, that was a good thing for us. So given those constraints, it sort of pushed us into potentially this serverless system, which is what we ended up going with. So at this juncture, what is serverless? And James Saryawani had a great talk yesterday that you should check out. He goes into a lot more details about this. But there are still servers. They're just not your servers, which was good for us. There's no IP address that you can log into the machines. You can't run package updates and security patches. You can't sort of log in and execute your code. It's ephemeral computing. In our case, we're really talking about functions as a service, where we're literally defining a Python function that gets executed when some event happens. And all the magic to support that happens behind the scenes. So most of the major cloud providers have these functions as a service. We ended up using Amazon Lambda, but there's plenty of others out there. And again, literally, there's events that happen, maybe a file update or a batch of logs come in or a timer goes off and your function executes. So why is that kind of a big deal? Well, in the sort of iron triangle of features and time and cost, we really wanted to deliver on the features. We knew that cost was something we could better manage with this serverless infrastructure, since we're essentially paying for exactly what we use. Now, we may not be writing it in the most efficient way necessarily, but we see exactly the cost for the compute that we're consuming. So it's very measurable in that sense. And also the benefit here is that it scales as our product scales. And that's taken care of for us for the most part. The other aspect is the time to deliver here is shortened for our case because we're not managing these clusters of machines and security, the security infrastructure. So we were able to think about the code to run our models, not about where this code is running. And Python in the serverless world happens to be a pretty first-class citizen. We can run Python 3.6, which is what we develop in. You could run PowerShell in Amazon Lambda if that's your forte. And essentially anything that runs in like less than 3 gigs of RAM and that you can package up into 100 megabytes, you can run in these functions. So we talked about our constraints. We talked about what serverless is. We talked about Python in this serverless world. So where does machine learning fit into this? So I want to be very clear that this is not talking about the research and development of the models, not talking about the training of the models. This is very much what do you do once you have a trained model and you want to run data on it in production. In my opinion, that for a data scientist is a tremendous amount of work. It is very much a steep learning curve to overcome. And so hopefully this is a way that might make it easier for you, potentially. It's answering the question of, I've trained this great model, now how do I show it to other people? And in a certain sense, this talk is kind of a cop-out, because I'm saying, well, design this machine learning system and then just put in serverless components, which is kind of true, but it does make things easier, in my opinion. So as an example application, which is essentially the application we're running, we have two pieces of this pipeline. And in our case, we're processing events coming from websites, and we're running a classifier on those events to figure out, is this from a human or is this from a bot on the website? And our application is made a little bit simpler, that these events are discrete events with which we can build features and run a classifier on. In your case, you may need to do some temporal feature calculations or features with state, in which case maybe your feature construction is a separate function that talks to a database. But in our case, we have some amount of compute that reads in events, figures out the features, and turns those features into a score. And then we have some amount of compute processing to run business logic to figure out what we want to do about those scores. We have some kind of database to store them. And then on the far right, we want to serve those scores to clients. In our case, this is a fleet of network computers that call home to an API. So what we're doing here is, this is kind of the application, and we're using serverless products from Amazon in this case to make this work in a serverless world. So compute is the Lambda functions. So we got 3 compute functions here. We're streaming events, scores and events into these functions. This is Kinesis. We're having a DynamoDB database. And then our API gateway is Amazon API Gateway, which allows us to respond to thousands of requests per second and execute functions when those come in. So in code, pseudocode, stepping through those 3 compute functions we had, our first compute function, which is, this is very much what it looks like in code, just with more boilerplate, where the event that happens is that there's a batch of events that gets passed into our function. We iterate over each of those events. They make the features from the events, call the classifier, and we get a score that we send to the stream. So it's a very compartmentalized function to run the classifier and sends those scores back out. Then there's another function that decides what to do with them. Again, it's receiving a list of scores. We iterate over those scores. There's some business logic to say, do we care about this score? If so, we write it to the database. So that's that first half of the pipeline, classifier to storage. And then the third piece is the client interface. So you can imagine a client like doing a curl request to an API where they want scores. And literally what we have is a function that when a API event comes in, we say, well, what kind of event is it? And well, it's a send me a scores event. Then we grab the scores from the database and we return them. So those are our 3 compute functions. And then I wanted to have just a little bit deeper dive on the classifier side, because this was pretty powerful to us, is that we wanted to have code to define our pipeline, but essentially the model piece, we really didn't want to have to do a complete new deploy of code in order to change the model. So what this looks like is that Lambda is creating a container that runs for, 5 to 15 minutes, depending. And it's has a Python virtual machine that stays in memory, so you can do some caching. So in our case, when the classifier function is invoked, it checks to see, do I have a model in memory? No. Do I have it stored on the local disk? No. If I don't, then it calls out to S3, downloads it into memory, and then it can be used for a couple more requests. What that also allows us to do, which is at the bottom, which half of you can't see, is that this provides a pipeline for data scientists to release new models. So if I train a new model and I think it's ready for production, I can serialize that model to disk, send it to the S3 staging bucket. And then I have another function that says, oh, there's a new potential model. Let me download it. Let me make sure it's got all the correct endpoints. Let me maybe run some events through it to make sure I don't get nons coming out. And then maybe send some reporting. Maybe I want to send an email to the team to say, hey, are you ready for this model to go to production? And the team can approve it. And then that function can move the pre-production model into the production environment. And through an environment variable change in our production classifier, just tell it, hey, next time you run, there's a new model for you. And all that happens sort of hands off. And so as a data scientist, I could release new model versions as quickly as I wanted, essentially, without having to change the pipeline code, which is pretty cool. So a little bit of a demo application. This is a much simpler application, and this is just a client sends a request to the classifier with some data. Classifier executes and returns the data back. If you can get to that URL, you could play with it. So what this looks like, sorry for the tiny font, is I have here, it's hard to read. Take my word for it, it's a 40-line Flask app. And in this case, I'm using a project called Zappa that makes it really easy to turn a Flask app into a Lambda function. Amazon's Chalice also does this. It may even do it better, but I haven't tried it yet. I'll try it when I get home. And all this Flask app is doing is it has two endpoints. The one that renders the page, which is going to be a web form where you can play with the features. And then there's a prediction endpoint, which takes those features in, runs my model, and spits back out a score. And then the model itself is loaded on the module level when this code is loaded into the Lambda environment. Yes, OK, so what that looks like is, so over here, I have my URL, which is available to everyone if the internet works. Otherwise, I'm going to have to connect from my phone. And, oh, there it went. So I think it went. So you saw that took a little bit of time. That was the infamous cold start problem where my function had to bootstrap a little bit. But now subsequent calls should be pretty quick. So they're coming through in like, yeah, 100 milliseconds. So every time I hit refresh, what is happening is the Lambda function starts, executes that Flask app, and finishes, and it's done. And I paid for the 100 milliseconds that it ran. And then the other piece of this is every time I check one of these, so this would be like an example healthcare app where you can change the patient's features, and it updates the probability that that patient is going to have a bad day. So if their basal heart rate is, I don't know, 1,000, we'll see what happens. Oh, well, it doesn't think they're going to die, so, you know, maybe I need to work on my model a little bit. Yeah. We can see over here on the right, each time I change this is just some JavaScript, just calling the prediction endpoint with literally the features in the form. Then it runs the Lambda function, and
I think you haven't checked the patient history of hypertension.
Oh, maybe that's it. I don't know. We'll see. Well, it got worse, so. Anyway, so just over here on the prediction endpoint, you could call this directly if you wanted. So you can see I got all the features encoded up here. This person had a moderate history of cigarette usage. I don't know, we can change it to, I think it's heavy. Got a little bit worse. So maybe cigarette usage doesn't play a lot into this model. But again, I want to emphasize that nothing is running right now, and I'm not paying for anything until I hit refresh. It calls the prediction endpoint, returns the value, and then it's done. And to release this, which I won't do now, this is a Docker container. I can simply do like a Zappa, Zappa update dev, which you can't see. And it downloads all the Linux wheels, takes my code, zips it up, uploads it to Amazon, configures the API gateway, and then returns me a URL, and it's done. And it's like super simple to do. All the code's on GitHub. You should try it out because I think it's cool. So I got a few minutes left, I think. So just we talked that this is really the production side. So what about the training side? There is actually some efforts of people playing around with the serverless stuff to do model training and building. PyRen is a project where they're doing massively parallel computations, and they're getting some, I don't know, crazy numbers. They're running, say, 3,000 simultaneous workers and doing, I don't know, 20, 40 teraflops of compute. There's been a couple talks recently on serverless MapReduce, serverless Spark. So check it out. If you do this, do a talk on it, because I'm interested. Another benefit of this is that since we only pay for what we use, it makes it, really simple to stand up a full production and test pipeline that are identical. So it makes it nice for integration testing, where if you have this whole test pipeline identical to production, you can send in events, make sure the exact events you expect come out. You can even pipe in your live event stream to your test pipeline, make sure it scales up properly like you're expecting. And all of this is really convenient because you only pay for what you use. Some of the lessons we learned in building this thing is that logging is especially important in this type of environment. You don't have access to your server logs that you may have when you own the box. So doing a lot of logging has been helpful. Kinesis Firehose makes that pretty convenient for sending out logs and storing them in S3. CloudWatch was okay. Datadog was better for doing monitoring and alerting on this. And Datadog has some nice Lambda plugins, essentially, to make monitoring easier. Writing your infrastructure as code is hugely important if you can get in the habit of doing it. CloudFormation was not that great at the time I tried it. May have gotten better because it changes a lot. Amazon has SAM, which I think is trying to make that easier. And then Terraform was pretty good for writing this out as code. Again, we talked about a test and a prod pipeline. This one's important. There's no such thing as a free lunch. You still got to write good code, unit testing coverage, still have to have good code hygiene, and literally you pay for what you use. So if you screw up and write terribly inefficient processes, you're going to get billed for it, which is, good and bad. Finally, two things that I think are still difficult, and Chalice may make some of these easier, is build dependencies are kind of a pain. Like I'm building my dependencies in a Docker container to try make sure I get the correct Linux dependencies. Because if you've ever tried to install scikit-learn and NumPy and SciPy and pandas and then move it to a different environment, like it's non-trivial. That is getting a little bit easier. Integration testing is also kind of hard because your code is still running in a Lambda function, which has some magical bits. So if you really want an identical environment, you kind of have to use Lambda to do that. So in conclusion, the pipeline we built is still running. Right now we're doing, I don't know, a couple hundred events per second input, and then we got a bunch of clients, several hundred, returning a bunch of records per minute. We had some event over here on the right. That was this summer. I don't know if it was like a production bug or if it was an actual attack on a website, but over the weekend our input traffic skyrocketed. And nobody had to wake up with PagerDuty because everything just scaled magically for them. And you can see how it scales up and down over the weekends, all things that we like because we like to sleep. So again, the example app is here. The code's on GitHub. I'm on Twitter, or you can email me. If you're building machine learning pipelines, I'd love to chat because I think it's a cool space. And I can take some questions if you have any. Yes.
Yeah. So you said you didn't pay for anything until it fires. You're not using Glue. You're not using Kubernetes. You're not using anything that costs money per second.
The question was, are we paying for exactly what fires, or is there other costs? Yes, except for Kinesis, there's like a monthly cost per shard that's like $5 or something.
Not 44 cents a second.
No. Yeah, it's not 44 cents a second. So yeah, our whole pipeline is running on a few dollars per day.
That's amazing. So I would.
In the back.
Have you run into any issues with queuing of events or missed events based on like the cap that you have for number of instances that you can spin up to?
The question is, how do you deal with like lost events or backlog of event queues and all that business? The answer is yes. which is one of the benefits of having that full test pipeline, is that you can sort of test that out a little bit ahead of time. In our case, our application, we're not dealing with critical events like financial transactions, so we can drop a few if we need to. Lambda has a dead letter queue, which will let you know if they failed, so you could have a separate pipeline for processing failures if you wanted to. But yes, you still have to deal with those as engineers. Yes, here.
Thanks. Could you talk about Lambda versus Fargate? So in some cases, you're going to want to have a full-on container. I don't know what balance you found there.
So the question was Lambda versus Fargate. At the time we built this, our security team said that Fargate was unacceptable, so we didn't pursue it. They may have walked that back a little bit. So if we had to rebuild this, and so we're dealing with streaming events, so our classifiers are running nearly continuously. So in that case, it might make a lot more sense to go with something like Fargate. I don't know. You should investigate it and do a talk on it.
Okay, thanks.
Over here.
Yeah, I was just curious if you come up with any strategies or had advice on how to mitigate that cold start problem, which I assume is largely monoloading.
Yeah, the question was dealing with the cold start problem. Yeah. So, well, a lot of people write about this, so I am not the expert. One way that I think Zappa does it is that when it, and this is why I'm a little puzzled. So Zappa, by default, when you create a container, it has a little like 5-second timer in the background that just pings your container every 5 seconds to make sure one is live. So I don't know why my initial request took so long. But that said, if I were able to pull up our dashboards for latency and you plot it over time, you very much can see a 5-minute tick in latency where it's probably one of the containers shutting down and another booting. So I don't know. You got to just build your application with that in mind. Anyone else? Very good. Go get coffee.